So we're now transitioning from kind of classic object-oriented Java and functional Java to reactive Java and reactive programming. And so I thought I would start out by looking at an example here. This is an example that's in my GitHub repository, and I'll show you where it is here. So if you go into my GitHub repository, and which is the live lessons repository, and you go to RxJava, you'll find this folder. And even though it's in the RxJava folder, it's really showing kind of a Rosetta Stone that, as you can see here, shows how to download images from a remote web server or remote web servers via a whole bunch of different Java concurrency and parallelism mechanisms. And so we're going to take a look at how to do this stuff, and it'll be kind of fun because we can kind of compare and contrast sort of modern Java circa 2014 style techniques with reactive programming, which is a bit more, even more modern in some ways. So if we go back over to the folder, this is where all the files are. Let me first start running this thing in the background. It's going to take a while to run because it's doing quite a lot of stuff. So we'll let that go ahead and run in the background while we take a look at the code. So as I mentioned before, this example shows how to download images from one or more remote web servers using a bunch of different concurrency and parallelism mechanisms. And we're going to take a look at Java parallel streams. We're going to take a look at RxJava, and we're going to take a look at Project Reactor. And what's kind of cool about this is it will give us a way to compare and contrast those different approaches. Now, over the next few weeks, we'll be covering all the different mechanisms in RxJava and Project Reactor. So some of what I'm going to cover now really isn't covered in those lectures till later, but I want to give you a flavor of what you can do with those frameworks. And since we're going to show the regular Java streams approach and parallel streams approach first, hopefully you'll get a good glimpse of what the program is doing, which will make it easier to understand how to transfer or translate from functional programming Java to reactive programming Java. So here's what we do. We start out by initializing the options singleton. One of the few places I typically use singletons in my code is for processing options. You might like that, you might not. That's just my style. You'll notice also I'm saying how many cores are available. And if you take a look at what is run here, you can see that we start out with 16 cores. So I have a 16 core computer. It's not actually 16 cores. It's actually 8 cores, but they're hyper-threaded. And so there's plenty of things to do in parallel. First thing we do is we warm up some thread pools so that they're ready to go, and hopefully the test results will be more accurate. And then we're going to run a bunch of different programs showing off different features. So this is going to be all the Java parallel streams stuff. This will be all the Project Reactor stuff, and this will be all the RxJava stuff. And when we're done, we're going to print out the results sorted in increasing order from fastest to slowest. And you'll see there's a whole bunch of different mechanisms we're using to test to see which one works the best. So first, let's kind of see what this thing is doing. Here's the run stream tests file, or rather the run stream test method. And you can see here what it does. If we go to run streams tests, is it's going to go ahead and run a couple of different examples of parallel stream computing. The first one, as we're going to see here, is using the default Java fork join framework, which works in a particular way. By default, the fork join framework will have as many threads in the fork join pool, the common fork join pool, as there are cores that are known to the underlying execution environment, the virtual machine. And as a result, no new threads will be added when blocking I/O occurs. And that is important for the test, as we'll see. The next thing we're going to do is we're going to run that test again, except this time we're going to use a slightly different mechanism that uses Java managed blocker mechanisms. This is a topic that we cover in another one of my courses. I won't go into it in great detail here, but what the managed blocker does is it makes it possible to expand and then later contract the number of threads that are available in the common fork join pool. So it actually can adaptively grow the fork join pool to be larger as threads block. And then the third approach we're going to use is a variant of this that uses something called a blocking task. And the blocking task is a very cool mechanism that we use in order to be able to have a little wrapper around managed blocker so it's easier to program. All right, so let's take a look first at these different implementations. First, let's take a look at the streams test run parallel streams method. You can see it's used by all the different variants here. And what we're doing is we're passing in different method references, which we'll look at as well. And those different method references will use different techniques to download the images. So let's go ahead and take a look at this. So here's run parallel streams. And as you can see what it's going to do, it's going to first start the garbage collector to kind of get everything collected, because this is very memory intensive because we're downloading very large images. We then delete any images that were already there. And then if we're logging, we run one implementation that logs a lot of output. We're not going to do that for this, but it's fun to try if you want to see everything, all the steps are involved. If we're not logging, then we use this thing called test download streams. And test download streams, as you can see, is the function that's passed in. So this is literally a Java 8 function, which is a functional interface that has a single method called apply. And so we're basically using these things kind of like pointers to functions or pointers to member functions in C++ in order to be able to parameterize the way the behavior of this test program works. There's also a little helper method I have here called time run. And as you can see, what time run does is you pass in a runnable, or you can pass in, I think, a supplier, and it starts the timing, starts keeping track of the time. It runs whatever we pass in as the runnable, and then it stops the timing, and then it goes ahead and it puts into a map the execution time, which is the time between when we started and when we stopped, under that particular test name. So just a nice way to test the timing of everything in a very convenient way to do things. Okay, so that's basically what run parallel streams does. And then, of course, what we want to do is take a look at some of the various methods that we pass in here. So here's the test download streams method. And what this does, this is actually pretty cool. What it does is it uses Java streams to go ahead and get the list of URLs. This is what we're going to be using for our test program, our test purposes. Let's go take a quick look at that method. So get URL list goes and takes a look at all these names of images. So you can see I have a big array of names of images. There's a lot of images. I think there's something like 42 images here. And they're all located here on my website at Vanderbilt. And we convert those into a stream. We flat map them all together and turn them into a list of URLs. So we have a stream of URLs. We can limit how many there are. In this case, we want them all. And then we collect that into a list. So this is just using good old Java streams techniques. So we get a list of URLs as the result that comes back from get URL list. So we take that list of URLs, and then we use a neat factory method that's part of the Java Parallel Streams framework in order to convert that list of URLs into a stream of URLs that will be processed in parallel. And so we now have a parallel stream, and we're going to take each of the URLs that come out of that stream in parallel, and we're going to map it to the download and store image method, which is going to be one of several variants we can pass in, which will either be one that uses the default common fork join pool that doesn't expand itself, or two different variants where we use managed blockers in order to be able to expand the number of threads in the common fork join pool. So that is going to download and store the images, and then we're going to collect all these images into a list of images, and then we go ahead and print the statistics for this particular test run. And we'll take a look at what that looks like here. Go over here, you can see when this runs, it says, test default download behavior, downloaded and stored 42 images using 16 threads. It used 16 threads because that's the one that uses the default common fork join pool. So there's only 16 threads, no matter how many images there are. The other tests that we run have the expandable threads, so they will use more threads. They will grow the size of the thread pool so that there's basically as many threads in the pool as there are images being downloaded. And hopefully we'll see when we take a look at the behavior that might have a difference in how it behaves. It's often hard to know how this is going to behave, especially because it's running over my Wi-Fi network and it doesn't always behave the way we want. As you can see here, the fastest to slowest was using test adaptive MB download behavior. That's the adaptive one, and that's the fastest, and then other ones are slower. I would probably want to run this in a better network environment. Right now, I'm using my network also for Zooming, so there's a bit of collusion and contention for bandwidth. But I guess the key point here is that the adaptive version performed the fastest, and arguably that's because it had more threads in the pool. So this is basically just showing what the results are, and you can see that it prints the diagnostics out as things run, and then when it comes down here, it'll sort them from fastest to slowest. Okay, so that's what the output looks like. What I'd like to do now is pop up a level here and take a look at these different ways of implementing download and stored image. So this is by far the simplest way to do it. This is the one that just calls download image. And as you can see, what download image does is it makes a new image, and the contents of that image are going to be downloaded using this download content method, which just makes a byte array output stream and a new read buffer that's 4K size. And then it's going to get the input stream from the URL, and we'll then go ahead and read from that input stream 4K chunks at a time, writing to the output stream. And when we're all done doing that, we will convert the results to a byte array. So that's just a simple way to download a file. So that's what we do here. Nothing fancy. We download the image, and then we go ahead and store the image on the local device. And that's really quite simple. We just go ahead and open a file and then write the contents of the image to that file. The download and store image MB method, in contrast, uses manage blockers in order to adaptively increase the number of threads that are available in the common fork join pool, which is what we're using for the computation with parallel streams. And here's what it looks like if you use this API directly. You say fork join pool.manage block, and then we make a new manage blocker instance, and we override its block method. That's what's going to get called, which can block, because of course we're going to download an image, which could very well block. And when we block in block, then that will compensate by adding a new thread to the common fork join pool. So it'll keep growing, and it'll have more threading resources, which should enable the thing to work better because it can take better advantage of the CPU or the multiple cores. We're using a somewhat little sleazy trick here because I was too lazy to do something more fancy here, but we're basically making an array with one element in it, and that allows us to be able to store something in here, even though you really shouldn't do stuff like this. I'll show you a better way to do this in a second, but this is just a way to get it to work without having to do too much extra wrapping and facading and so on. The last approach here, which is also very simple to look at, is called download and store image BT, where BT stands for blocking task. And we'll take a look at blocking task in a second. A blocking task is a little wrapper that I wrote. You can see there's a file over here called blocking task that has a class called blocking task, and it has a static method called call in manage block. And as you can see here, we go ahead and download the image at that URL. And this handles all the underlying machinery necessary to use the managed blocker without exposing all the gobbledygook that we had up here to the programmer. So let's just take a quick look at blocking task. So here's blocking task. It's a very simple utility class that encapsulates a managed blocker. And you can read more about why it's done this way at this link. There's pros and cons, of course, but it's interesting to know it can be done this way. So here's the method that is really the hard, heavy lifter. It's called call in manage block. You pass in a supplier, and we then go ahead and we take that supplier and we wrap it in a local class called supplier manage blocker. We'll look at that in a second. And then we say fork join pool managed block, and we pass in the managed block local variable, and all the magic happens there. And when we're done, we then get the results from this. So let's go ahead and take a look at supplier managed blocker, which is a static nested class. And you can see that supplier managed blocker implements fork join pool managed blocker, and it defines a field called mSupplier, which is the supplier that was passed in, keep track of the result, which is parameterized type, and we keep track of whether we're done. And you can see the constructor just squirrels that supplier parameter away in a field. And then the block method will say supplier, mSupplier.get, which will go out and make the blocking call. We get the result back, we indicate that we're done, and then we return true. This call, of course, will block, and that will compensate by adding another thread in the common fork join pool. And then down here, get result just returns the result that we had, that we got and assigned in block. So just a helpful little class that allows us to write code like this, which is much more concise than trying to write code like that, which is more verbose.
Did you say this?
So that's basically the initial implementation. This is showing you how the various parallel streams implementations work. What we're going to do next is we're going to take a look at how we could program the same thing with RxJava.